This is a video from section 7.5. The directions say to evaluate the integral. We're going to go ahead and look at example 1. Suppose I had the integral from 0 to 1 of 3x plus 1 to the square root of 2 power dx. And whenever possible, I go for the u substitution. Okay? That's what I always start off with to see if I could even do that. And u substitution works for this one. So if I let u be 3x plus 1, I know that du is 3 dx. And so dx is 1/3 du. Okay? And we have to transform our limits in terms of u as well. So when x is 0, u is 1. And when x is 1, u is 4. And so I'm going to have a 1/3 out in front of the integral. I'm going to evaluate the integral from 1 to 4 of u to the square root of 2 du. So this is 1/3 times 1 over square root of 2 plus 1 u to the square root of 2 plus 1, and I'm going to evaluate from 1 up to 4. And so what I get here is 1 over 3 times square root of 2 plus 1. And when I replace u with 4, I get 4 to the square root of 2 plus 1. And when I replace u with 1, I get 1. Because remember, 1 to any power is 1. And now, you may want to check with your instructor to see if your instructor wants you to rationalize the denominator. That's always a possibility. So, and if you want to rationalize the denominator, it would look like this. Square root of 2 minus 1 divided by 3 times 2 minus 1 times the quantity 4 to the square root of 2 plus 1 minus 1. And that's just going to be square root of 2 minus 1 divided by 3 times 4 to the square root of 2 plus 1 minus 1. So it's probably going to be this line if they want the denominator rationalized, or it's going to be the first line, depending on how your instructor wants you to express your answer. Example 2. Suppose I had the integral of e to the arc sine x divided by square root of 1 minus x squared dx. So again, this is another u substitution. I'm going to let u be arc sine x. And I just happen to know that the derivative of arc sine x is 1 divided by square root of 1 minus x squared. And then I just attach a dx there, right? And so this is the integral of e to the u du, which is e to the u plus c. But u is arc sine x. So this is e to the arc sine x plus c. And that's example 2. Let's take a look at example 3. Now, suppose I give you this one. Suppose I had the integral of t sine of t cosine of t dt. And so I run through the combinations, right? Is this a power of sine and cosine? Not really, because there's a t located here. Would I solve this by partial fraction decomposition? Well, no, because it's not. No, because I can't break apart any fraction. I don't see a fraction. So it's not partial fraction decomposition. It's not a power of sine and cosine. And I don't see a u substitution anymore. And so the one thing that comes to my mind is integration by parts. And so you start to try to eliminate what you don't want to do. And then hopefully we focus on a technique that might work. And so I'm going to let u be equal to t. And dv is going to be sine of t, cosine of t, dt. And so du is equal to dt, and v, I hope we don't mind, this is going to be 1/2 sine squared t. And so this is going to be uv, which is 1/2 t sine squared t minus the integral of 1/2 sine squared t dt. And so we really want to remember that power reducing formula. And so this is going to be 1/2 t sine squared t minus 1/2 the integral. Now, sine squared t can be written as 1/2 of 1 minus cosine 2t dt. And so this is 1/2 t sine squared t minus 1/4 of t minus 1/2 sine 2t plus c. So notice I just took the 1/2 times the 1/2 and called it a fourth, and then I integrated what was in parentheses with respect to t. And so I'm going to simplify this a little bit. So we get 1/2 t sine squared t minus 1/4 t. So I'm just distributing the 1/4 plus 1/8 sine 2t plus c. And that would be the correct answer for example 3. If we take a look at example 4, suppose I give you the following. Suppose I had the integral of natural log of 1 plus x squared dx. Now, what I think about here is, can I do a u substitution? No, I don't think I have a u substitution there. Could I do partial fraction decomposition? I don't see a partial fraction decomposition there either. I don't see u substitution. I don't see partial fraction decomposition. So what I'm going to try is integration by parts. See, I really encourage you to try something. You may have to go back to the drawing board, and that's totally okay. And just because I'm doing one technique, that doesn't mean there's not another technique to be tried. It's always possible. And so here, I'm going to let u be natural log of 1 plus x squared. I don't call it dv because I don't even know how to integrate it. And so dv is dx. It's like 1 dx. So v is x, and du is 1 over 1 plus x squared times 2x dx. And so this is equal to x natural log of 1 plus x squared. And I'm going to subtract twice the integral of x squared over x squared plus 1 dx. So I do uv minus the integral of v du. So I'm going to teach you a little trick here. So I'm going to write this as x natural log of x squared plus 1 minus 2 times the integral. Now I'm going to take x squared over x squared plus 1 dx. And so what I'm going to do is I'm going to add 1 and subtract 1 to the numerator. And then I want you to watch what happens. So this is x natural log of x squared plus 1 minus 2 times the integral. And then I'm going to write this as x squared plus 1 over x squared plus 1. So notice I'm splitting off the fraction. And then I'm subtracting 1 over x squared plus 1. And then I'm going to integrate this with respect to x. And so this is x natural log of x squared plus 1 minus 2 times the integral of 1 minus 1 over x squared plus 1 dx. And so when I'm done, I get the following. I get x natural log of x squared plus 1 minus 2 times the quantity. The integral of 1 dx is just x. The integral of 1 over x squared plus 1 dx is arctangent of x. And if we're going into differential equations, we absolutely got to know that integral. And so if I simplify a little bit further, this is x natural log of x squared plus 1 minus 2x plus 2 arctan x plus c. And that was example 4. Example 5. Suppose I had the following. Oh, well, we're going to do this one. Suppose I had two x minus 3 divided by x cubed plus 3x dx. So we're going to have to do a little bit of partial fraction decomposition here. U substitution doesn't make sense. It's not a power of sine and cosine. Trigonometric substitution doesn't make sense here. It'd be, well, you could make it work, but it's difficult. The most logical one here is partial fraction decomposition. And so what I need to do is factor the denominator. So I'm going to factor out an x and write x squared plus 3, and I'm integrating with respect to x. And so I'm going to take 2x minus 3 divided by x times x squared plus 3. And so this is a over x plus bx plus c divided by x squared plus 3. So when you have a degree 2 on in the denominator, you have to have a linear term, or you have to have a first degree in the numerator, shall we say. And so the LCD is x times x squared plus 3. And so I need to multiply both sides by the LCD. So we get 2x minus 3 is a times x squared plus 3 plus x times bx plus c. Now, 2x minus 3 is a plus b times x squared plus cx plus 3a. Now, I got to equate coefficients, and so we have 3 equations. Now, a plus b must equal 0 because there is no x squareds on the left-hand side. When you have x here, I have c equals 2 directly. And then when I have a's, the constant terms, I have 3a equals negative 3. And so therefore, a equals negative 1. And if a equals negative 1, then that tells me b must equal 1. And I'm in business because I'm going to come over here and I'm going to rewrite this as follows. Now, a is negative 1, so this is the integral of negative 1 over x. And then I'm going to add x plus 2 divided by x squared plus 3. And this is with respect to x. And so I'm going to split off the second fraction here. And so I'm going to write this as negative 1 over x plus x over x squared plus 3 plus 2 over x squared plus 3 dx. So this is a great partial fraction decomposition. And so this is negative natural log of the absolute value of x plus, if we do a u substitution on the second term, we get 1/2 natural log of x squared plus 3 plus. Now, this is an arctangent problem. And so this is going to be 2 over square root of 3 arctangent of x over root 3, I claim, plus c. Now, we can convince ourselves by taking the derivative back again. And so I'm going to go d dx of 2 over root 3 arctangent of x over root 3. So this is 2 over root 3 times 1 over root 3 times 1 over 1 plus x squared over 3. And I don't know if you notice, if I multiply numerator and denominator by 3, I get exactly what I need up here. So this is correct. And this was example 5. So I definitely needed to do a partial fraction decomposition. For sure. So if we take a look at example 6, suppose I had the following. Suppose I had the integral from 1 to 4 of e square root of t divided by square root of t dt. So I'm going to let u be equal to square root of t. du is 1 over 2 square root of t dt. And so 1 over square root of t dt is 2 du. Now, when t is 1, u is 1. And when t is 4, u is 2. And so this is the integral from 1 to 2. I'm going to pull the 2 out in front, and I'm going to integrate e to the u du. I hope that looks okay. And so this is 2 times e to the u from 1 to 2. And if I plug that in, I get 2 times e squared minus e. And I'm done. So it's a nice little u substitution problem. And so you can see in this section, they vary greatly in terms of difficulty level. I want to show you this one. Suppose I give you this one. Suppose I give you x divided by 1 plus square root of x dx. Now, this one doesn't fall under any sort of category, shall we say, but I always like to get rid of radicals. And so I always start off with some type of substitution like this. Because if I square both sides, I get u squared equals x. And directly speaking, I could say dx is 2u du. And then I want you to notice what happens. Now, I'm going to write this as 1 plus u for the denominator. In the numerator, I get u squared, but I'm going to multiply by 2u du. And I'm going to pull the 2 out in front, and I have the integral of u to the third divided by u plus 1 du. Just like this. Now, what I could do here is I'm going to do long division. So notice how the degree in the numerator is bigger than the degree of the denominator. So let's fill in the missing degrees. So we have u cubed plus 0u squared plus 0u plus 0. Now u goes into u cubed, u squared times. So we get u cubed plus u squared. If I subtract, I get negative u squared, bring down the 0u. I know that sounds a little silly, but it helps me keep track of where I'm at in the division process. Now u goes into negative u squared minus u times. And then we get minus u squared minus u. If I subtract, I get u, and then I'm going to bring down the 0. And then u goes into u one time, and then here we get u plus 1, and if I subtract, I get negative 1. And so why did I do that? Because what I want to do is I want to write this as twice the integral of, I'm going to take u squared minus u plus 1, and the remainder is negative 1. So I'm going to go minus 1 over u plus 1 du. So let me have a little divider here. So that's what I got when I took u cubed divided by u plus 1. And so this is 2 times 1/3 u cubed minus 1/2 u squared plus u minus ln of the absolute value of u plus 1 plus c. But remember, u is square root of x. And at the same time, I'm going to distribute the 2 in. So I get 2/3 times x to the 3/2 minus x plus square root of x minus natural log of square root of x plus 1 plus c. So remember, I'm taking square root of x and I'm raising it to the 3rd power. So that was what was happening on that type of question. That was example 7. Let's take a look at one more for this video. If we take a look at example 8, suppose I give you this one. I'll stick to the same theme. Suppose I give you this one. Square root of x e to the square root of x dx. So this one's very interesting. Now, I'm going to let u be square root of x. Square both sides to get rid of the radical. Standard practice. And so dx is 2u du. And so this is the integral of u e to the u. And so I'm going to replace dx with 2u du. 2u du. So I'm going to pull the 2 on the outside, and I'm going to integrate u squared e to the u du. And this is classic integration by parts. So I'm going to let w equal u squared. dw is 2u du, and dv is e to the u du, and v is e to the u. And so this is equal to 2 times. I'm going to go u squared e to the u minus the integral of 2u e to the u du. And so if we do this all over again, we'll call it r equal 2u, and dv equal e to the u du. And so dr is 2 du, and v is equal to e to the u. And so this is 2 times u squared e to the u minus, in parentheses, we get 2u e to the u minus the integral of 2e to the u du. And so this is 2 times u squared e to the u minus 2u e to the u. If I distribute the negative in, and if I integrate, I just get 2e to the u. So I get plus 2e to the u plus c. But u in the beginning was square root of x. So this is 2 times x e to the root x. And then I get 2 root x e to the root x plus 2e to the root x plus c. And that's a good stopping point. And this is concluding the video for section 7.5. And we worked over 8 examples in essentially the review of integration. Thank you.